Alright guys, welcome back. This time we take a look at cooling channels introduced to our upper and lower die. So these cooling channels, please remember, it's an axisymmetric problem, so it's almost impossible to create these cooling channels using machining type procedures, unless your name is Elon Musk and you own a special boring company which can like bore around tight corners. But if you're not, then you probably will rely on additive manufacturing to introduce such kind of channels into your dies. So you can think of it as a spiral, right? So these holes are technically connected in a spiral-like shape, which is then not 100% axisymmetric, but we ignore this for a second. Some other things we ignore for a second. Later we will consider the cooling capacity, let's say, of the liquid that we are running through the channels to be infinite, meaning we can define a sink temperature, but we'll take a look at this later. So technically, if the fluid is starting in the center and flowing outwards or vice versa, it will heat up during the process and will have a locally different temperature. You could actually define this by given, let's say, 25 degrees here, 35 degrees here, 35 here, 45 degrees here. You could do that, but just for the sake of simplicity, we'll skip all of this or ignore this. So if you talk to experts when it comes to hot stamping, they will tell you actually one interesting thing, and this is what we like to take a look at today. They will say, why do you even bother with or about cooling channels? Because they say they simply have no effect on the rate by which the sheet is being cooled down, because the dies have such a huge volume, and also the metal-to-metal contact enables a fast transmission or conductance between the sheet and the die. So it's basically, again, the contacting surface which mainly dominates the cooling rate of the sheet. And we want to just check this statement and see if it holds up. So for that sake, we have a reference simulation, which was the one without cooling channels. And then we introduced 4 cooling channels on both the upper and lower die. So if we look at the results, we will first take a look at the reference simulation without any cooling channels being introduced. We'll check the nodal temperature. I've done some, and we changed the path a little bit. So we defined the first 2 seconds to be the forming step. Then there are 2 seconds of constant compressing from the upper die to the lower die, and then there is the retraction phase, which is again 0.9 seconds. So we just extended the contacting phase, the resting phase between resting bitches of the dies. So let's take a look at some of the results. So for instance, if we just take the temperature. Okay, so that is the reference temperature distribution. You see the contact phase, so you have the forming phase and then the contact phase, and then again, it's basically what we talked about in the first video, just a little bit extended. All right, so first, and it took Manish and me a couple of hours to understand all the details of it, so we only show you the results, but that's the beauty of finite element simulation. You are being presented with a result that you don't understand, and then step by step you check the physics behind it, and then you come up with a conclusion, and that's pretty interesting. So it's basically, I will start with the outcome of our analysis, and the outcome of our analysis actually is checking what happens if you only introduce the cooling channel and don't do anything else. So you just simply drill the holes in there, and the rest you keep constant. So this is what I want to do with you right now. So first we are interested in the maximum temperature again, and we go to a similar state, which is at the end of the contacting phase. Let's say at 4.1 seconds. We do the same with the cooling channels introduced. So that's roughly the same time span. And then we want to see again the location here. And what we see actually is that the temperature with the cooling channels being present is higher, and at least the maximum location. And you can also see some differences. Okay, let's give a uniform scale for both the simulations, so then it becomes easier to compare the two. So you can clearly see that also the sheet temperature in this case it's lower, the maximum is higher. So there are already some interesting observations just by introducing the cooling channels. And you can also see the distribution of the cooling channels, the temperature between the two is affected just by the cooling channels being there. So that's, I would say, a first interesting result to observe. And next on, you would ask, okay, how do I, and this again is for me probably the most important topic when it comes to being a simulation engineer, is this where you need to think about how to do it. And in this case, it is, how do I properly define my boundary condition? Okay, we said, okay, we run a fluid through here, then you say, okay, I can simply define, let's say, 25 degrees Celsius boundary condition at my cooling channels. And so this is what we did here. And you can see, we'll switch to the same time frame roughly. And you can see again that it's, what is quite interesting again is that the maximum temperature is again altered, it's lower, and also the overall temperature of the sheet is lower, which you would expect since there is a cooling defined at the edges. However, what is most striking is, and here it's technically also correct, that you see the temperature distribution in the die is very different. So here the heat was more evenly distributed. However, think again, so the dies do not dissipate heat to the ambient. So where does the heat go? And if we let's give 27 as the maximum temperature for both the simulations. So remember, we specified 25 degrees Celsius at the edges. So you can clearly see that defining 25 degrees C, it is maintained because it is a boundary condition that must be fulfilled while solving the thermal equilibrium, or the thermomechanical equilibrium, I should better say, right? In this case, of course, they heat up to whatever value. However, keep in mind that since no heat is technically lost in the dies because they don't radiate to the ambient, it is just you redistribute it. So, and think of it, is this the correct way to model the boundary conditions if the heat is not being taken away from the system but only redistributed? Your answer should be no, it isn't. So because defining a fixed temperature only means that in this it's like a rigid body. You tell the equations there they have to be 25. Whatever you do in the rest, it's according to your other boundary conditions. This means the inflow of heat due to the conductance with the sheet, and no outflow because there's no radiation to ambient. So right, again, I'm saying that you alter the distribution. But if you want to take something away from the system, you don't use, this is without. Let's go. So what I just talked about was that I define, I'll click on resume here. So what I talked about was this type of, you have a temperature type boundary conditions and you define a fixed magnitude. But this is not what we want to do. What we want to do is we want to define an interaction, which is a surface film condition. Because here you can see I've selected the 8 cooling channels, technically the inner surface of those cooling channels, and I defined a sink temperature. So at the surface, you can imagine having an inside and an outside. So the inside of the surface is the sink temperature, which is 25 degrees C. But this 25 degrees C is not part of your body. The outside surface is part of your body, but the flow from the outside of the surface, which is part of your body, to the inside of the surface, which is not part of your body, is defined by the film coefficients, like a conductivity coefficient you can think about. And so we ran 2 simulations, one with a realistic value of 3 according to our unit system, and one with an unrealistic value of 3000. And I now want to show you the results step by step. So we start with the one that has the realistic film coefficient, which is also lower than, wait a second, I need to go to the same time step, roughly here. And you can see, let's go to that the temperature distribution looks again more similar to the case where we defined no boundary conditions rather than the one where we defined the fixed 25 degrees as you see on top. So why is this the case? Why didn't introducing the film condition doesn't really affect our results? And for this, we again fall back to our heat flux analysis, which is pretty interesting because it can tell us a lot about what's going on. And here, if we look at let's say this, the cooling channel in the middle, we can observe a phenomenon that a lot of the heat is flowing around. I mean, here in the top, it's partially flowing around and partially flowing into the sink, but a lot of the times, and you can also see this here on the left, the heat is flowing around my cooling channel. So why is this the case? If we go back and check our model definitions and our film coefficients, our conductivity coefficient was defined to be 3. And our internal conductivity, so just from the material, the 22 MnB5, our internal conductivity we defined as 40. And according to just simple thermodynamics and general the flow of energy, it will follow also the path given the same delta and temperature. Let's assume our body has a temperature of 25 degrees somewhere here and the sink has 25 degrees. Then the flow of energy will be according to that of least resistance, so to speak. This is a little bit figuratively speaking, but I hope you get the idea. So it is more easy for the energy to flow within my die rather than leaving it on the surface towards the cooling channel, right? So it is just 10 times more likely because you have the internal conductivity of 40 and the conductivity between the metal and the cooling channel was set to be 3. Okay, let's compare it with the one where we defined 3000, which is way too high artificially speaking, and we'll come back, or we get closer to our actual solution. Okay, let's start with the nodal temperature again, and we see that in this case the result is kind of a mix between our falsely defined 25 degrees boundary conditions and having no or a low boundary condition. So in this case, let's go again to the right point in time, which is about here, and take a look at let's take a look at the flux as well. We see now that the flow of the heat is actually at the surface. In the best case, it's perpendicular. It means that the majority of the heat flows towards the sink, right? Because now with this artificially high film coefficient, it is just more likely for the heat to flow into the sink, and the sink is actually taking away the energy from the system, other than compared to the 25 degrees boundary condition. Even though they look similar, it's technically something very different. So again, I want to compare the, let's say, the falsely defined boundary conditions with the one where we did it artificially wrong. So both of the cases I would consider to be incorrect, but they yield similar results. That's interesting. However, in the one case, in the lower case, where we have the boundary conditions defined, we did it, let's say, not considering the outflow of energy to the cooling channels. So we just forced, we forced the overall energy within the dies to follow a certain path. So not the one that gets close to the cooling channels, but rather around it. And the same actually holds true if you activate the cooling channels and make it an actual sink so that the energy will flow into it. But opposed to this, it will actually be taken away from the system. So if you look at this, it's similar, but no energy is leaving the system. So it's technically a little bit different between the two. But, and again, I want to get back to the very start, comparing no cooling channels to cooling channels with a realistic boundary conditions. So what we've done so far is analyzing and understanding what type of boundary conditions lead to what result. And even though we would expect a certain results, meaning that our sheet is being cooled faster, or that the average temperature at the end is lower, we now come back to what the expert said in the beginning, right? Why do you do this? It doesn't really do much. And if we really take a close look at the results of this, we see that they might be actually right, because given only small, we can go to maybe 250 here and 250 here. We see actually that the highest temperature with cooling channels and realistic boundary conditions is even slightly higher than in the case without cooling channels. And we've proven that this might be correct by introducing cooling channels with no boundary condition, right? So just that you took away material close to where, in the case of no cooling channels, there is material which can take in heat. In the case of a cooling channel, there's no material which can take in that heat. So actually, we can conclude that the experts are right, at least given our task, which was run this thing once. But I just started two simulations, which I'm now looking at for the first time, because I thought, okay, what is if you do this repetitively, let's say 100 times, then over time your dies will heat up, because we still assume there's no way to radiate away the energy. So if you repeat hundreds or dozens of hundreds of these forming operation, which might actually be the case in a manufacturing company, what I did, I defined an initial boundary condition of 300 degrees C for the dies, and I now want to take a look at the results, at least for two different film conditions, because we've seen that in this case it might be actually the case. Maybe I should run another simulation without the cooling channels. Alright guys, so much for the commercial break. Welcome back, and we're looking at the results of the two simulations that I mentioned before. So at the bottom we see the simulation where the dies start out at 300 degrees C, assuming we had a lot of forming operations and we didn't have the time so that the dies could radiate away the heat, so they would accumulate the heat and just increase the temperature over time. So this is why we started at 300 and the sheet again at 600. And so this is after the retraction phase, and on top we see the simulation using the realistic film coefficient from the die to the sink. So actually we could argue that what we see at the top is now fairly realistic, as is the one we see at the bottom, just one with and without the cooling channels. So a couple of things to consider here. So even though the film coefficient is realistically small, there is still energy flowing into the sink, right? Because it accumulates, flowing, so to speak, flowing around it, right? You can see it. And once it flows around it, it can also flow into it, right? So this is what you observe if you look around closely around your cooling channels. A couple of other things to observe. Now, for the first time, let's check the location of the maxima here for both cases. So here now, for the first time, on top, the maximum is actually at the center, which is farthest away from any cooling channel. So maybe I should show you where the closest, which is here, but in all the other sections, one is closer, right? So it makes sense that now at the center of the body, at the center of the axisymmetric problem, there is the highest temperature. Whereas in the case on the bottom without cooling channels, we still have it in this, let's say, middle section of it, as we've seen before. And a couple of other things to consider here. Let's keep the limits in the lower case, the minimum at 300. So what you see actually is, and it's the same that you've observed in the other case, that your die further heats up because it still takes in energy, heat, from the sheet. So it started out at 300 and now it's above 300. If we do the same here as well, we see that most of the body is below 300 except those areas which, like in this case, you can see here on the in the left corner and upper right corner, there you don't have any cooling channels close by. So, but since, let's say, the heat transfer is fairly uniformly, if you look at the bottom here, you can see this. So within the contacting area, it's fairly uniformly. So in the areas where you don't have any cooling channels to suck away the heat, it makes sense that your body heats up. In the other areas, it cools down. So let's specify the maximum here and the minimum here. So it's kind of like the inverse. You see here it's been above 300, and in the other cases it's below. Let's say according to the cooling channels, here it's now 200 degrees C, which is fairly realistic. So in this case, a realistic film coefficient, like it can be based on water in steel pipes, can be the convective one, but still it's fairly low compared to the internal conductivity. It still has an impact, right? And this is what I wanted to show you. So this is what I really like about FEM simulations. By altering all these things, you can understand a lot of factors. So talking to the experts, they say, well, don't bother about cooling channels, you don't need it. They are right, but given certain circumstances, it still might be interesting to introduce them even in sheet metal forming, right? If we do bulk metal forming, it will be a different story, and this will be a story for a next video as well. But we have seen, or we have learned so many things today analyzing these simulations, so that the placement of the cooling channel is very important, that just the sheer existence of the cooling channel has an effect, that the definition of your boundary conditions is very important, especially if you operate with closed systems, so that in this case meaning that the dies are not radiating heat away. All the results will look a little bit different if you activate radiation to ambient, but you will see, given a realistic or radiation coefficient for this case, the impact is not super significant. So I hope you've just followed me through all the analysis, and that you try to just appreciate or focus on the stuff that you can actually use FEM simulations for, right? It's not about finding a result, but understanding the physics that lead to a certain result, right? The result, this is why you do FEM in the very first place. You want to get a certain results. You want to know how do cooling channels affect my temperature or my cooling rate, and then you see, then the answer is always it depends. But as a simulation and process engineer, you should be able to use this wonderful tool that Abaqus or FEM is in general to get behind the physical effect. What is going on? So looking at the nodal temperature might not be sufficient. Sometimes the heat flux is what gives you insight into it, right? The distribution, play around with the limits here. So this might help to get to certain insights of what's going on. Yeah, and the beauty is now you can just, if you set up those simulations, you can quickly start them, play around, and understand so many things that are out there. And once again, I would like to shout out a big thanks to Manish for helping us today. So Manish, if you want to say something.
It's my pleasure. So so really I have learned a lot doing the simulation, especially doing the analysis, which is, I would say, quite complex when we're including extra temperature fields also. So as you have already told.
So I think the interesting part is that even Manish, just by doing this, he actually learned more about those things than I did, because I just look at the results and try to understand it, but sometimes I can, even not working with it, understand even more, because it helps me to have like an outsider perspective and question all the steps and see, have you thought about this type of boundary condition? Let's talk about this. So this is always, find a colleague, talk to them. Exactly. And this is where you also find mistakes. Like most of the cases, defining boundary conditions or interaction properties, right? There are so many things you can do wrong, and usually talking to someone helps to identify these problems, and don't present the facts, rather let them dive into your simulation setup and try to reiterate what you have done and say, okay, maybe that's not the way I would do it. And by that you can, in many cases, identify mistakes early on, which help you later, because at one point you need a strong, validated simulation setup based on which you can do all your parameter variation and your extensive parameter studies. Because if the starting point is faulty, then everything that comes after that will be incorrect as well. So really make sure that your starting point, your initial simulation is really thoroughly set up and is physically sound, and in best case maybe even experimentally validated, and then you can play around with the parameters and actually use the tool FEM the way it's been intended to be used. All right, guys.
One small thing I would like to tell before closing the video. This is most important, because what we have actually told, how we can define whether the temperature is Kelvin or degrees just before doing this. So this is one thing where you can actually check it in the modal attributes. You can edit it, and these two are very required when we are doing a thermomechanical simulation. So
yeah, so we have promised at the very beginning of the session to show you this, and at the very end.
And this is the first thing you need to start actually by doing the thermomechanical simulations to tell us whether you're using, or tell the Abaqus, not us, whether you're using the degrees or...
You can also tell us, it's totally fine.
Yeah.
So you use the unit system including milliwatts and millimeters, right?
Yes.
Okay.
So it's up to you whether you use what type of units, but always keep constant throughout the simulations, and make the zero temperatures accordingly if you're using degree centigrade or Kelvin. That's
all right. I think that's a pretty nice concluding statement.
Units are always important.
Units are always important, and don't forget to activate Stefan and Boltzmann. And all right, guys. So much for today. Talk to you in the next week. I hope you enjoyed it. Click like and subscribe. I've heard it helps us to grow further and spend more time doing this funny stuff. And yeah, Manish, maybe see you around next time.
Yeah, sure.
All
Definitely.
right.
Yeah. Bye.
Bye.